So we're starting to move on from our basic understanding of polynomials, and we're going to start using polynomials to create other functions, namely what we call a rational function. A rational function, or we're going to call them sometimes rational expressions, we'll use that somewhat interchangeably. You can see the root word here in rational is ratio, and of course a ratio is a fraction. So what we're going to be doing is we're going to be taking a fraction, creating a fraction out of polynomials, have a polynomial in the numerator and a polynomial in the denominator. And that's going to create together a rational function or a fraction. So as a definition, a rational function is any function of the form, I'm going to call it r of x, which is a function notation, equals p of x over q of x. So it's another function over another function here. And the two functions in the fraction are each polynomials. Okay, so I'd say where p of x and q of x are polynomials. And there's one really important condition. In a fraction, you can never have the denominator equal to 0. Okay? And so if the denominator is equal to 0, you get an undefined value. So in a function, if the denominator is 0, it's also undefined. So, so p and q have to be polynomials, and that bottom polynomial, q of x, cannot equal 0. Cannot equal 0. If it equals 0, you have an undefined value for the function. Okay? Now, a rational expression is simply the right side of the function, right? It's not the function notation. You ignore that part of it. The rest of it, right here, the two polynomials, would be the rational expression, all right? So that just gives you an idea. So just a couple of quick examples of some rational expressions. Things like 2x minus 1 over x squared plus 3, right? That's a ratio of two polynomials, one on top, one on the bottom. Something like x minus 7 over x plus 2, right? That's a ratio of two polynomials. Of course, in any of these examples, the denominators cannot be 0, right? We have to have the case where the denominator is not 0. Interestingly, in this first one, I have a square, something squared, which is always positive or 0. Adding 3 to it, well, if you take a positive number and add 3, you're going to be more positive. You're not going to be 0. If you take 0 and add 3, you're going to be at 3. You can't have a negative. This will never end up being 0. So this one's okay. But this one here, the bottom can be 0. Namely, if you plug in a negative 2. So here, you cannot have x equaling negative 2, because if you did, the bottom would be 0. Okay? Okay, so that satisfies both conditions. And we can have, smaller polynomials, linear ones, even constants if we wanted. We can have bigger polynomials. We can have 5 terms, a 5th degree polynomial. We can have lots of things in here. And we'll see some that are larger polynomials show up. Something like 1 over x is a rational function. It has a polynomial on top and a polynomial on the bottom, technically. Okay, and of course in this one, that denominator cannot be 0, so you'd have to have the condition on there that x is not 0. Okay? If x were 0, you'd have 1 over 0, which is undefined. So this idea, this condition then, gives us some restrictions on the domain of a rational function. So if I had a rational function, of course, the domain is all the things you can plug in. But we're now seeing some numbers that you cannot plug in because they make the bottom 0. And so anything else will work. Polynomials themselves have all real number domains, right? So individually, they have all real number domains. It's just the numbers that make the bottom 0 will make the entire rational function undefined. So those have to be excluded. And so as a result, the domain of a rational function is all real numbers except those that make the denominator 0. Okay? So that's going to be your domain. So anytime you have a rational function, if you identify the numbers that make the bottom 0, those are the things you exclude from the domain. Okay? Okay, so let's take a look maybe at a couple more examples of this. We'll get some more complicated ones. Oh, I missed an L on rational, didn't I? Yeah, there it is. Okay. Okay, so let's take a look at something. We'll do R of x for rational function. I won't always use R of x. I could use f of x or g of x or whatever I want there. For this one, I'll use R of x. So R of x equals maybe x squared plus 7 over x minus 4. Okay? So on this particular function, we could find some values. We could find some function values, and we could find the domain. So there's a bunch of things we could do here. First of all, let's look at some function values, like f of 1, for instance. If I were to plug in a 1, then I just get 1 squared plus 7 over 1 minus 4. 1 squared is 1. 1 plus 7 is 8. We get 8 over, and 1 minus 4 is negative 3. And of course, 8 minus 3, or 8 over negative 3, sorry, is negative 8/3. So you could just leave it as negative 8/3. It's also negative 2 2/3. Okay. You could try like R of, I don't know, 0. You could plug in a 0. If I plug in 0, I get 0 squared plus 7 over 0 minus 4, which is 7 over negative 4, or negative 7/4. Right? Same as negative 1 3/4. Or we could even do something like R of negative 3. Let's try that one. If I plug in negative 3, I get negative 3 squared plus 7 all over, well, that's a ugly looking fraction bar there. Let's straighten that out. All over negative 3 minus 4. Well, this will be, negative 3 squared is 9, so 9 plus 7 all over negative 7, which is 16 over negative 7. None of these are working out real nicely to whole numbers, but fractions are fine. So that's equivalent to negative 2 2/7. Okay, so we can find function values. All we do is plug in the input, calculate an output. Okay, you might get them to reduce nicely to whole numbers or integers. Some of them will just be fractions. No problem with any of that. Now let's look at the domain of R of x. Okay, so the domain of R of x. Again, the domain is found by finding all values that make the bottom 0 and excluding them. So in this case, I would take x minus 4, set it equal to 0, and solve. Now, it's kind of obvious from this that 4 is the number. But again, you could add 4, you just solve the equation, you get x equal 4. Well, of course, that's not the domain. That's what we want to pull out of the domain. And so the domain itself is all real numbers except 4. Okay, so we can write it out in words, But remember, with domains and ranges, we often use set notation or interval notation to represent those. We saw that several chapters ago. And so now what we're going to do is try to build this into an interval or a set. Now the set notation is actually not too bad, the set builder. You can just write x, again it's x values because it's a domain, x such that x is not equal to 4. That would be sufficient for me, okay? You're basically saying all numbers except the 4. Now as an interval, it's a little bit tricky. To see how the interval works out, get rid of this definition. To see how the interval works out, I'm going to draw a number line that excludes 4. Okay, so think about that on a number line. If I had the number 4 on here and I wanted to exclude it, so I put a circle on it, or I could put parentheses on it, whatever. But I wanted to include everything else. That's everything to the right and everything to the left. I'm really looking at 2 intervals, one to the left of 4 and one to the right of 4. That is really on an angle, isn't it? That's okay. The one on the left is the interval from negative infinity to 4, not including the 4, so I need a parenthesis there. The one on the right is 4 to infinity, again, not including the 4. The infinities never get included. Now this is a compound inequality or a compound interval. Looking at a union, remember we did this in chapter 4 when we looked at those compound inequalities. And so because we're looking at points that are in one or the other or both, we use a union or a U symbol between them. There's not really any other nice way to represent this as an interval. So we have the set form, the interval form, and of course a number line. But you'll be asked on MyMathLab and on a test to do one of these two. I believe MyMathLab really likes these interval forms. Okay, so correct me if I'm wrong. It could be that they'll go with some of these set forms, but I think the interval form is going to be the more common one on MyMathLab. Okay, so anyway, that's your domain for this one. Now, if I change the function up, I could get some more complicated denominators, and that will create more complicated domains, or more numbers potentially to pull out. So an example might be something like f of x equals x minus 5 over x squared plus 7x plus 12. Okay. In this example, I have, my numerator is linear, my denominator has a degree 2, we call those quadratic. And if I want to find the domain of f of x. Well, the domain of f of x is found by simply taking the denominator, setting it equal to 0, solving that equation, and then pulling those numbers out or excluding them. So here, what do we have? A polynomial equation. Didn't we just learn how to solve those in a previous video, where you factor the left side, factor the polynomial, set the factors equal to 0 and solve. Okay, so here, a polynomial equation I want to factor. It's a trinomial with a lead coefficient of 1. So factors of 12 that add up to 7 are what we're looking for. They would of course be 3 and 4. So I'm going to go x plus 3, x plus 4. Those two factors multiplied make 0. And of course, the zero factor property says if two things are multiplied together equaling 0, then at least one of them individually must be 0. We then, of course, solve each of these equations, and we get x equal negative 3 and x equals -4. Okay, so those two values are the two values we must exclude from the domain. So the domain then is going to be in set form, all values of x that are not equal to -3 or -4. So such that x is not equal to -3 or -4. Now I just put a comma in there. You might see some people are a little bit sticklers about writing -3 and x equal -4 or something like that, but this is fine. In interval form, which I think is what my math lab is going to want, it's a little bit harder because now you're pulling two numbers out. So when you pull out, and if you think about this, if you pull out, oops, -4 is to the left of -3. Don't forget that, by the way. On the number line, you always want to put the smallest one to the left. You're excluding both those points, but including everything else. So now we're going to actually end up with 3 intervals. One on the left, one in between, and one on the right. And you have to accurately represent those 3 intervals. So the first one is -∞ to -4. The second one runs from -4 to -3. And the third one runs from -3 to infinity. And of course, it's a union of all 3 of those intervals, so we have to include a union symbol between them, okay? So the final domain is either the set form or this interval form. Again, I believe my math lab really likes those interval forms, okay? Okay, so that's just kind of the basic idea for a domain. Again, you're just going to take the denominator, whatever it is, set it equal to 0, solve the resulting equation, and exclude those numbers. Okay? Okay.